Ever wonder how a computer can recognize your face in a crowd? Or how a simple spreadsheet can predict next month's sales? These everyday marvels are powered by two different but related approaches: traditional machine learning and deep learning. While both share the fundamental goal of generalization, which is the ability of a model to perform accurately on new, unseen data, the way they think and the fuel they need are vastly different. In this video, we are going to dive into the architectural foundations that make these technologies work, comparing everything from their internal structures to their massive data requirements. Whether it's a single mathematical curve or a distributed network of neurons, we are unpacking how machines turn raw data into intelligent action. Deep learning is a specialized subset of machine learning that utilizes large, multi-layered artificial neural networks to model complex data. While both machine learning and deep learning share the fundamental goal of generalization, they differ significantly in their internal architecture, how they process information, and the resources they require. One of the primary distinctions lies in how data is prepared. Traditional machine learning relies heavily on manual feature engineering, where data scientists must personally select and refine the most relevant dimensions of data before an algorithm can process it. Feature selection is the process of choosing which specific aspects or variables of the data are the most important to use, and feature extraction is the process of refining raw data into its most relevant dimensions before it is ever fed into an algorithm. Deep learning, however, operates on raw data and automates the feature extraction process. This automation makes deep learning far more scalable for complex tasks, though it often results in models that are less interpretable than traditional methods. The structural approach to problem solving also varies. Traditional ML uses explicitly defined algorithms such as linear regression or support vector machines, which often aim to find a simple mathematical curve to represent data points. Deep learning uses distributed networks of nodes or neurons inspired by the human brain. These networks utilize nonlinear activation functions to act as universal approximators, capable to reproduce almost any complex function by combining an arbitrary number of small, adjustable lines. The fuel and engine required for these systems are vastly different. Traditional ML can function effectively with smaller datasets and standard CPU processing power. In contrast, deep learning requires massive amounts of data and significant computational resources, specifically graphics processing units. This is necessary to manage the volume and granularity of updates required for the millions or billions of model parameters, such as weights and biases, during the train phase. While traditional ML optimizes a small set of parameters to minimize loss, deep learning employs the backpropagation algorithm. This allows the system to compute exactly how every single individual node in a massive network contributes to the overall error. By using gradient descent, the system can make precise adjustments to every weight within the entire architecture. To better understand these differences, think of traditional machine learning like a custom-built toolkit, where craftsmen must personally select and sharpen every chisel and hammer before starting a project. Deep learning is more like a factory assembly line. It requires a massive amount of raw material and expensive machinery to set up, but once it is running, it can automatically refine that raw material into highly complex finished products, without the craftsman needing to manually shape every individual part.